Okay, so today is one of those days. I think in Quantum 2 we talked about your baby book, like when you're born, and I don't know if they do it in other countries or not, but a lot of times in the U.S., people keep baby books and write down big events in your life. Like the first day you rolled over, the first day you crawled, or whatever. Today's one of those days that you want to put in the baby book, okay? Because today we're going to get to the point where we're able to actually, see all this hard work we've been doing for the past few weeks be put, into a usable format. Okay.
Yay.
Yeah. Okay. So we'll start to make sense of it all. You guys know who that is? The picture.
Is it you?
Huh? Is that me? Jesus, man. It's like the 70s. No, this is Feynman. That's Richard Feynman. And I'm guessing that's some type of family vacation.
Shagging wagon.
Yeah. Oh, this van is at least last time I was there.
Diagram.
It was at Fermilab. They had it sitting out in front of Fermilab.
Huh.
I think it's a permanent display now. But if you go there, it's there. You can see it. It's Feynman's van. Yeah, it's really famous because it's got Feynman diagrams all around it. But yeah, anyways, looks like it, but it's probably Southern California because he was at Caltech. But yeah. Okay, so let's kind of recap where we are. I'm just going to recap in words. Okay, so what we have so far, or where we've gotten to, is that we're able to compute this thing called the generating functional, right? And the generating functional can be complicated. It can be, this double Taylor series expansion monster of an equation, or we can represent the generating functional as, an expansion in diagrams, right? In diagrams that we can just write down and draw, okay? And so that's what the generating functional here is denoting, is that we can write this thing as an exponential of the sum of all diagrams, right? But not all diagrams, because we saw last time that we had to neglect vacuum diagrams, right? That was because, why did we do that? Because, I remember. Yeah, because, infinities, right? We wanted to get rid of infinities, right? And the other one was we had to neglect diagrams with only one source. Okay, and again, that was again because you had these infinities, but that one we canceled with a counter term that we write down in our Lagrangian that we're allowed to write down. Okay, so that's where we are. Okay, so we've got the generating functional, and we know from our discussion, weeks ago when we first started talking about path integral, that the way, the thing that we're after, remember, are these correlation functions, right? These time-ordered products of operators. Okay, and we've seen that the way to compute those guys in the path integral formalism is by taking functional derivatives, right? Okay, so using the functional derivative trick. Okay, so we're going to see that in action, and you'll hopefully you'll be reminded of that trick. Okay, all right. So what I want to do is I want to start by considering the exact propagator. Okay, so what do I mean by exact propagator? I mean, I think I wrote it down last time. A propagator from one space-time point, you can call it x1, to another space-time point, x2, right? But we want to consider the exact propagator. Okay, so that means that we would have to draw in a blob in our diagrammatic way of writing things, and anything can be going on in that blob. Okay, as long as the diagram's connected. All right, so you can have all kinds of loops and all kinds of crazy stuff going on. Okay, so anytime you see a hat on this guy, you know that I'm talking about the exact propagator. The propagator computed to all orders in perturbation theory. Okay? Because what we're going to do is we're going to, obviously we can't compute this guy to all orders, so we're going to have to make some approximations. Okay? So to denote the exact propagator, I'm going to use that caret or whatever you call it, hat. Okay? Okay. All right, so we want to compute this propagator. Remember, it's just the 2-point function, and we've seen that to compute these guys, we want to use a functional derivative trick, right? So to simplify the notation, I'm just going to rewrite our functional derivative just as a delta, okay? Just because you're going to see it's going to get really messy if I didn't, okay? So anytime you see delta sub I, it means functional derivative with respect to j, where its space-time point is denoted by x sub I. Okay. All right. So let's go. Let's compute the 2-point function. Okay. So I have got the 2-point function. Get some factors of I. Okay. Here's my generating functional. Okay. I'm going to take 2 functional derivatives, and then in the end, I'm always going to set j equal to 0. Okay. That's just the recipe for computing these things. Okay, so first thing I do is I plug in for z. Okay, so z I plug in exponential I W function, right? And now let me start carrying out these derivatives. So when this guy hits this, it's going to give me what? The derivative of the inside stuff and the original function back, right? And then I can carry out the delta 1 derivative. So these are just like normal derivatives, right? It hits this guy. So you got one term where the W function is being hit by both delta 1 and delta 2. And then I've got the other one where delta 1 would hit the exponential and brings down this guy, the delta 1 acting on acting on W. And then I would have the exponential there, right? But I know that I'm setting j equal to 0. So what I've done, and we know in the j equals 0 limit that this exponential goes to 1. Right? So in the last line in equation 4, I've dropped the exponential, okay? Because I carried out my derivatives, and I know that I'm setting j to 0, so the exponential goes to 1, so why keep writing it down? Okay? Make sense? Okay. All right? So this is what we have, okay? These guys on their own, in the second term, the delta 2 acting on W and the delta 1 acting on W, these are what we call single source terms, right? We saw these last time. We know they're single source terms because after you carry out the delta 1, right, and you set j equal to 0, the only diagrams that are going to survive are going to be the ones that started out with only one external point, right? Okay, so these are called single source terms, okay? And we saw that these, by our prescription are 0. Right? This is basically the VEV, and the VEV, we always tune it to be 0, right? Because that's one of the conditions that the LSZ formula requires of us. Okay? Michael, someone trouble? All right?
Yeah.
Okay. If it kind of something bothers you, let me know.
It's not. It just seems like the whole thing goes to 0.
No. Because this is what, this would be, here, when you expand it out, you're going to pick out the 2-point function.
Oh, yeah.
Right?
Oh, just the second term.
Yeah, just because this first term is being acted on by both delta 1 and delta 2. Okay. All right, so that's a kind of a big revelation that you can, when you're computing these things and you see single source terms coming out, you can just go ahead and you can just drop them. Okay, so when we compute the 4-point function, you can drop those because you know that you're going to tune your parameters such that the VEV is 0. Okay, so that means that the 2-point function is just the term where you have both the derivatives acting on W. Okay, and in the end we set j equals 0. Okay, and so but I think I've said it a couple of times now. So, diagrammatically what we have is something that looks like this, right? And the way you can think of these deltas, the functional derivatives, is what they do is they basically strip off, beforehand. So this might be x and y, right? And then you're acting on this with delta j of x, let's call it x1, and delta, oops, we don't behind the screen, delta j of x2, right? And what was I going to say? Oh, yeah, and these guys, if you wrote down their factors, would come in with factors of j of y and j of x. Right? And so what these functional derivatives do is they basically chop off these external points, right? And they not only chop off the external points, but they label the what's left of the external point by what their argument is. Okay, so you might start out with something general from point x to point y, but those functional derivatives are going to strip off the endpoints and they're going to label it with their argument. Okay? All right. The tricky thing is that, in general, we don't know if x1, the time x1, occurred before x2 or if x2 occurred before x1. That's why we put that time ordered operator in there. And so what the time ordered operator tells us to do is carry it out, all possible ways, right? And so what we have, basically in the end, so when we take the functional derivatives and we sum over the two ways that you can do it, you get something that looks like equation 6. Okay, so this is kind of a representation on the left-hand side, the diagrammatic representation of the propagator. Okay, so notice it's got the hat on it, so that means it's the exact guy. And we're representing it as a perturbative series in the diagrams. Okay, and so what I have is, this is what we would call tree level, right? This single diagram, there's no loops. Okay, so no loops means it's tree diagram, plus higher orders. Okay, so I'm just neglecting the higher orders for now. We'll compute those later on. Okay, that's a whole other beast. Okay. And one interesting thing to note is that, the factor of 2 that you get, because basically when you compute this guy, you compute that guy, they're the same thing, they're the same number, right? So you basically get 2 times one of these, right? But, if you had computed the symmetry of this diagram, you would have found that it was 2, right? Because if I think of this as 2 external points and a propagator, right, I can get the same diagram by flipping the propagator and or flipping the derivatives at the external points, and so that gives me a symmetry factor of 2, right? So in the beginning, I would have had, a 1/2 out here, right? But these diagrams add up, give me a factor of 2, and so it cancels off that symmetry factor. Okay. It seems trivial, but it's important. It's an important result because it's telling us that when we consider tree level diagrams, we never have to consider symmetry factors. Okay, and we'll see it more explicitly when we do the 2-to-2 process. Okay, what else? So what we have mathematically is, so you'll see in my notation, a lot of times I put this, it uses equals with a dot. I don't know what it really means, but I like to use it to denote, some factor is equal to diagrams. Okay, I've seen it used before, but so I don't know. Anyways, so mathematically we have what? So on the left-hand side, I've still got the exact propagator, and now I can write down. I know what this is, right? In terms of the objects that we have, it's just the Feynman propagator. Okay. And so I have the exact equals first order plus higher orders. And I guess that's where we stop for that. Okay? Right? Because now we know how to compute this delta. Right? We've seen how to compute, at least we did it for the quantum mechanics case. But we could compute that and get a number or some function if we wanted to for x1, x2. Okay? Okay. So like I said, we'll come back to, hold on. My wife's asking me if we need milk. Let's see. No. Okay. All right. All right. So that's the 2-point function. Let's consider next the next time order product of operators. And that would be time order product of 3 operators, which is 0. Good. Right? It's 0. Any time order product of odd number of operators is 0. Right? So that was a trick statement. Okay. So we can skip right ahead to the 4-point function. Okay. So I want to consider the time order product of phi 1, phi 2, phi 3, phi 4. Right. And the way I get that is by taking the generating functional and applying 4 derivatives. Right. 4 functional derivatives. Okay. So this is all just carrying out the chain rule. Is that the chain rule? Yeah, chain rule. Right. And along the way, I'm probably dropping single source terms. Right. Once I get down to, oh, no, I don't. So I get down to here. Okay. So I've carried out delta 1, delta 2, delta 3. Right. Or delta 2, 3, 4. Carried it all through. You can see I've got some single source terms. I've got some 2-point, or two. What do you call those? Two source terms, and so on and so forth. Okay. Right, and I can take delta 1 and I can drop any terms that have single source terms. Okay, and you can see like this guy is kind of an admixture. It's got two sources, one source, 2 source. Right, so these diagrams, if they contain even one factor of a single source diagram, you can drop it, or single source term. Right, so that leaves us with this. Okay, so it's looking a little bit more manageable. I've got one term, I've got all the functional derivatives acting on the W function. And then I've got 3 other terms where I have 2 derivatives acting on W, and then another term that it's being multiplied by another term where the other 2 are acting on another W. Okay? All right? So this doesn't look half bad. Okay? And so this is about as far as we can take it for the correlation function. What we want to do now is take this and plug it into the LSZ formula. Okay, so we're basically doing 2 to 2 scattering. All right. Okay, so we've got 4 external legs. All right, so those 4 external legs are represented in equation 8 by these 4 functional derivatives. Okay. And so let's plug this into the S matrix, or the scattering amplitude, okay? And that is given by the LSZ reduction formula. And to remind you guys of the beauty of the LSZ formula, I recreated it here, okay? So what we want to do is we want to take that, equation 8, plug it in here, and start taking some derivatives, okay? What, did I say something funny?
No.
It's just too short.
Huh? It's what?
I said it seems too short to plug that one into that one.
Too short?
Yeah.
I'm going to show you how you don't have to do it. I mean, you do it, you have to do it, but in the end, you'll see a lot of stuff drops out. Are you saying because I'm skipping a bunch of steps, or?
No.
No. What do you mean by too short?
She's being sarcastic.
Oh, okay. Oh, I got you. Too simple?
Yeah.
Yeah, okay. All right, sorry. What is today? It's my Friday, okay? So it's my Friday, even though I had the week off today from those lovely children. Okay, so let's see how this works, all right? So we want to take equation 8, plug it in equation 9, okay? And what do I want to do? Okay, so let's consider one term. Let's look at one term, and then we'll work out the others. But first, let's consider the first term on the bottom line of equation 8. Okay, and these are we just worked these out, right? These are the 2-point functions, right? Right? And so so this term is a product of two 2-point functions, all right? One has arguments x1 and x3, right? The other one has arguments x2 and x4, okay? Right? So we would take where we have that, we would plug it in there, and then that would get plugged into here, okay? And now, what do we know about the Feynman propagator? It's the blank function of the Klein-Gordon equation. It's the Green's function, right? And the Green's function, what happens when it gets hit by this guy? If it gets hit by this operator, del squared plus m squared, then we get a delta function, okay? So you can see now the beauty of this, because now what's going to happen is I'm going to plug this stuff in, and these guys are going to hit these guys and give me delta functions. Because if you look, I've got a crap load of integrals I got to do, right? Okay, so let's do that. All right, so we plug it in, okay? And that's what it looks like, okay? And before I do that, I define these things that I just call F, so I can make it a little more, I can put it on one line, okay? Any equation you can put on one line, you can do, right? That's why I think I did that, okay? So we have these F functions that look like this. They're just the Feynman propagator being operated on by the Klein-Gordon operator, okay? And this is a typo. This should be, this xij should be xi minus xj, right? Okay? But like we just said, these the Feynman propagator is the Green's function of the Klein-Gordon operator, right? So what that tells us is that we're going to get some delta functions out, okay? And when I do all that, when I carry that out and I use those delta functions, the smoke clears, okay? And I end up with equation 13, all right? So you guys can imagine, everybody can imagine that happening, right? That I take this thing, right? And what do I have? Oh, I use the delta functions coming from here, right? And then I'm left with this derivative, but then I can start to use, what do I do? I do some trick where these guys are going to give me some delta functions, right? Because they're the integral representation of the Dirac delta function, okay? So in the end, I get all these delta functions, and I get 2 left over, okay? For this particular case, I get a delta function that tells me that what? K1 has to be equal to K3, and K2 has to be equal to K4. Right? Right? And then I get these factors of 2 pi to the 4th that always come along for the ride. Okay? All right, so what happens is these the other terms in our equation, so the delta 1, delta 2, acting on W, so that's, I need a damn stick. So this guy, right, and this guy basically give you the same thing, right? You just have to interchange the labels, okay, as what we just found there, okay? But we've seen these guys before, right? When we talked about, what were we doing? When we were doing the simple harmonic oscillator, right? We worked it down to, diagrams, basically writing on diagrams. And these are basically, so they're given by these diagrams, right? So what it's telling me is that the momenta, so if we label these, so let me go back to this picture, right? So I have, let's assume that we're doing some scattering, right? And I know what the momenta of the initial particles are, right? Because I'm shooting them out of a gun or something, right? And then I can measure the momenta of the final state particles, right? Right. So what it's telling me is that so what is this one? It's K3 is the same thing as K1, and K2 and K4 are equal. All right. So what it's telling me is that there's no scattering going on, right? Because if they would have scattered, K3 would be something different than K1, right? All All right, so what it's telling me is this one term represents a diagram, or the diagram represents that term that looks like K1 goes to K3 and K2 goes to K4. All right, they don't interact. Okay, and the other two terms would give me similar things. So they would give me, there'd be one where K1 would go to K4, right, and K2 would go to K3, right, and then there would be another one where K1 goes to K2 and K3 goes to K4. Okay, so these are non-interacting diagrams, right, or diagrams for no scattering. Right? But these are boring, right? Because what we're interested in are scatterings, right? We want to see what happens when we smash shit together, right? So what we can do is we can say, okay, I don't even care about these diagrams, right? Because they're not representing any of the scattering, okay? And so what I can do is I can just say, I don't even want to touch those guys. Those guys are dead to me. And I'm just going to consider diagrams that involve interactions. Okay? And so diagrams that involve interactions are going to be what we call fully connected. Okay? Fully connected means that you can get from one point in the diagram to another point in the diagram by following the line. Okay? You never have to jump off. Like I could never do that for these non-interacting diagrams. Like I couldn't get from K1 to K4. Right? There's just no way. Okay? All right, so what we can do is we can just say, all right, from now on, if we're interested in the results of scattering, right, particles scattering off each other, we can just focus on what we call the connected correlation function. Okay, and it's going to look exactly the same as before, except we're going to put. So let me go back to where I was. Okay, so here's equation 8. Right, so we're saying that the last three terms in equation 8 give me no scattering, right? So I can drop those guys, okay? And then to remind myself that I'm only concerned about fully connected diagrams, I put a sub C on the left-hand side, right? Just to remind myself. And on the right-hand side, all we're left with is the W function being hit with all four functional derivatives, okay? Everybody good so far? Okay, all right. All right, so this is what I want to use in the LSZ formula, okay? So all those other terms that we were putting in, we see that they end up giving us no scattering, so we don't even need to bother with them. All right, so this is the guy I want to put in there. Right, okay? So remember, W is what? It's a sum, right? Of diagrams, right? We're represented as the sum of diagrams, okay? And a perturbative series, right? And so it's going to have diagrams, it's going to have a tree diagram like this guy. It'll have it'll have diagrams with a bunch of loops and so on and so forth, okay? But the point is, the only guy that's going to contribute to this scattering are the diagrams in W that have 4 sources, right? So we can just focus on the J equals 4 terms. Right? Because anything less will get, killed by derivatives, right? Which sounds like a good movie title. And any terms that have more than 4 J's will be killed by J equals 0 line, which is not a good movie title.
That's the sequel.
Sequel.
It's
Killed
never-
by
it's
the,
never
yeah.
better.
Yeah. It's better?
Sequels are never bad.
All right. Okay, so what we can do now is we can represent the W, the I times W, as diagrams, right? We would write down diagrams that have 4 points or 4 external sources, right? And so let's consider the lowest order. Well, at lowest order, there's only one diagram we can write down, and it's this guy. That's fully connected. All right, that's always important to keep in mind. Okay, and so what we would do is we would take this diagram, we would write out, we could match it to the term in our double Taylor series expansion, right? And then we would take these functional derivatives. Right? But what you're going to find is that when you do that, there's actually because you have four functional derivatives and the different ways that you can do it, there's 4 factorial ways of carrying out these derivatives. Right? So there's a factor, so you get 24 ways, basically, to carry out these derivatives. Okay? And so that means that there's going to be, in general, 24 diagrams to compute. That's a lot. That would be bad. Okay? But you have to ask yourself, are they unique? And it turns out that they're not. Okay? So if you go through, it's a good exercise to, maybe do that, or maybe you don't maybe not have to do all 24, but write out a lot of them and write down what they would be in terms, using Feynman rules or going back to the double Taylor series expansion and seeing, how they would be represented, and you'll see that you would get the same expression for different diagrams, right? So that means, in terms of diagrams, that would tell you that there's duplicates. Okay, so there's only 3 that have distinct what we call topologies. Okay, and each group contains 8 diagrams. That 8 is important because why? What's the symmetry factor of one of these diagrams? 8, right? So in general, we would divide by 8 because this diagram has a symmetry factor of 8. But we see that each of these diagrams, there's actually 8 of them, right? And so those 2 factors of 8 cancel each other. Okay? So this is, again, another example of tree level diagrams. You can take, your symmetry factors and you know what you can do with them, right? Toss them out the window because you don't need them. Okay? All right, so what do I want to do? Yeah, okay. All right, so now let's go back. So let's look. We have a diagrammatic representation of this scattering at lowest order, and now let's go back to our double Taylor series expansion. Okay, and we see what? Well, we want. This is what order in G. It's second order G squared. All right, so if I look at the double Taylor's expansion, I've got G, I'm going to have at least V equal 2, right? And V equal 2 means I'm going to have 6 functional derivatives, but I want 4 to be left over, right? 4 J's left over. So that means I need P to be 5, right? Because that'll give me 10 factors of J. And after I carry out those 6 functional derivatives, I'll have 4, okay? That sounds horrible.
Yeah.
Right? So let me just show you what the answer would look like. Okay? So if I take, what the hell am I doing here? Let's see. So basically I'm expanding, right? And I take those functional derivatives, okay? And it leaves me with these 3 terms, okay? You see I've got a common delta, common Feynman propagator that I pulled out front. And then it's a product of 4 direct or Feynman propagators. Okay, but we still are integrating over these space-time points y and z. Okay, y and z, if you look back at how I labeled those, are the kind of internal points, right? Okay, we're getting there. We're getting close to writing down Feynman diagrams. We'll never have to look at shit like this again. Okay. All right. No, what are we going to do? Okay, so we want to take this and plug this into the LSZ formula. Okay, equation 9. All right, so let's remind ourselves what equation 9 looks like. All right, it's going to be a mess, right? We've got 4 of these Klein-Gordon operators operating on our correlation function. Then we've got this exponential that's got 4 arguments. And then we have 4 integrals. Okay, so it's going to be a mess, it looks like. Right? But we remember that each of these guys, these Feynman propagators, are the Green's functions, right, of the Klein-Gordon operator. Okay, and so what that does is it's going to eliminate, again, a lot of these integrals, and then we can actually do a lot of these integrals because they're trivial once we got the direct delta functions in hand, and they look like something like this. Okay, so this is the full scattering amplitude. All right, so remember how we got here. We're considering fully connected 4-point diagrams. Okay. All right, so I've got this expression. Okay, can I take it any further? Before, when we were computing the 2-point function, we basically got it to about this point, and we said, okay, that's enough. All right. So let me see if I can take this a little further. Okay, and I can take it further by plugging in the Feynman propagator in momentum space. Okay, this is a big step because we're for the rest of this class going to work basically in momentum space. Okay, so we're making a transition now. I think in Peskin, if you look in Peskin, he'll give you the Feynman diagrams or the Feynman rules in position space, right? But they're ugly, right? And it's really cumbersome to compute things in position space. And so what we do is work in momentum space. Okay, so let's work in momentum space and replace that Feynman propagator by the form that we computed. I don't know how many last week. I'll just say. Okay. And so what happens is you got this denominator that's going to sit outside, but this guy is going to combine with the exponentials inside the brackets. Right? Okay. And at that point, what you have is the only x and y, only y and z dependents are going to be in these exponentials. Right? And these guys are just going to give you delta functions. Right? They're just the integral representation of the direct delta function. Okay? So once I make that simplification or that exchange of working in momentum space, a lot of these integrals go away, right? Because they're just delta functions. Okay? Everything on that slide clear? Okay. Okay, so what I end up with is my the integral and the denominator that came from the Feynman propagator, right? And all those other integrals we've done now, using Dirac delta functions or using the integral representation of the Dirac delta function. And I end up with this, 3 terms that look like products of these delta functions and a bunch of factors of 2 pi. Okay? But now, I've got these delta functions, I've got a 4-dimensional k integral, I can do the k integral, right? And I end up with this, okay? So I can only use one of these guys, so one's left over, okay? But in each case, you can commit yourself, in each case, when I do this integral, or do one of the integrals, I'm going to get this common factor of delta 4, k1 plus k2 minus k3 minus k4. Right? What's this delta function telling us? Exactly. We saw this when we did scattering in quantum mechanics. There it was a delta function in the energies, I think. Right? But that told us to conserve energy. Right? Here we're working in Minkowski space, so energy and momentum are basically the same. Right? So this guy is telling us, no matter what the diagrams look like, make sure you conserve energy and momentum. Okay? And it will come out, any process that you calculate, you better get that Dirac delta function out. Okay? Okay? And so what's left over are these 3 terms. Right? From those 3 terms, we get these 3 denominators. And you can see where they come from because you got the denominator out front, and when the Dirac delta functions act, they change k into k1 plus k2, and so on and so forth. Okay?
Each of them is like property.
Yep. Yeah. That's where they came. Yeah, that's where they came from. If we go back here, right? Well, they're coming from products of what we call a propagator, right? That go from one point to another. Okay.
You don't call these terms?
Yeah, we will. Yeah, you're spoiling it for everybody else, though. Okay? No, I'm just kidding. Another thing to note is is there an I epsilon in equation 21? The correct answer is yes.
Yes.
It's there. Okay, remember, and everything we do, whenever you see m squared, and it's in the denominator like this, it's m squared 1 minus I epsilon, right? Because we have to shift the Hamiltonian, right, to use to be able to compute the time order product between the vacuums, right? Okay?
So it's the mass of the propagator or the mass of the particle that we try to describe.
It's a mass, but it's not. It doesn't necessarily have to correspond to the physical mass. We'll get to that when we get to loops. But for now, it's just the mass of the particle. Okay.
Which one?
Well, we only have one particle in this theory. We only have phi's. Everything's made of phi's.
Right, so it's also.
But yeah, it's the parameter. Where does the parameter come from? We'd have to go back and look at it. But yeah, it's a free parameter. At tree level, you can identify it with the physical mass. Okay, the same mass of the particles going in.
Yeah. So phi is, in addition to the propagator, is the particle that we also scatter.
Yeah. Yeah, because we only have one particle. So yeah, so our diagrams, so like that first diagram, I think we had something that looked like this. All right, so we have, this represents phi scattering through what we will eventually call an S channel. But the only particle we have access to in our universe is phi. Okay, and so it goes through a phi into two more phi's. Okay, that makes sense.
Since we are in phi cube, each vertex has 3 branches.
Mm-hmm.
That's phi.
Yep.
If we were in phi fourth, each vertex would have.
Yeah, we wouldn't have this diagram. We would have at tree level. We would just have one diagram that looked like this. Yeah. Yeah. But we're living in the 6th dimension in 5 cubes, 5 cube theory. All right. Okay, so the final, we have basically everything we want, right? I mean, this is the scattering amplitude, and I told you that we know what K1 and K2 are, and we can either measure K3 and K4, or we can just sum over all possible values. Okay, we'll see how to do that later. But this is the scattering amplitude, right? Now all we have to do is take that modulus, square it, and we can go back to quantum mechanics to see how to compute the cross section, right? Or a differential cross section. I'll cover it again, I think, but this is it. This is what we link directly to an observable. Okay. Right. So this is another point where this delta function, this energy momentum conserving delta function, and this factor of 2 pi to the 4th will come in every calculation that you do, every scattering calculation that you do. Okay. So what we do is typically factor that out. So this is called the S matrix. Remember, we called the scattering S matrix. Okay. So we'll factor that stuff out and define a new matrix called the T matrix. Okay. And, all right. So the T matrix is defined by just stripping off the stuff out, the constants, or that constant 2 pi to the 4th and the delta function out of the S matrix. Okay, and then K in and K out are just the total incoming and outgoing momentum. Right. Okay, so this is the point where we've done a couple of calculations. Right, we've seen how difficult it can be when you're taking functional derivatives, especially as you go up in the number of legs or the number of external lines, right? And or if you compute loops, it's going to get really tough. Okay, so this is where Feynman is going to come to our rescue, and let's take a 2-minute break, and when we come back, I'll write down the Feynman diagrams and we'll check and make sure that we can get the same expression we just got. Okay? All right.
You wanna come over on Saturday?
I don't know. Saturday? No, wait. Saturday, no.
Saying you wanna come over on Saturday? Austin, typically, like twice or three times a month, my wife or Sean and I like to have people come over and just hang out. We play games, and usually we make dinner for everybody on Saturday. You like to come over?
Okay, this Saturday. But keep in mind me all the time.
Yeah, we're gonna speak to the leader this time. Because it's hard to feed like, because we're having a lot of people come to the game. It's a lot of fun with for people, but it's hard to feed everybody. So,
Or you can say, each room,
yeah, I guess. But I feel like that's something.
we did it.
8 rooms and 360.
What?
Uh,
Sure. What time?
You still have one? I don't think I do.
Alright.
All right. All right, so this is the moment that we've all been waiting for. Okay. Drum roll, please. Thank you. All right. So we want to get rid of this cumbersome formalism, right? It just totally sucks. I hate it. So I want to come up with a better way of doing things, right? An easier way of doing things. All right. And so that's what Feynman did. Okay. So Feynman worked out a few of these guys and saw that, hey, wait a minute, I'm seeing a pattern here. Okay. And he worked out, a diagrammatic way of representing these scatterings. Okay. Represent being the key word there, like Tim and I were talking about the other day. A lot of people think when you write down an S-channel diagram like this, that's what the particles are actually doing, and it's not. Okay, this is just our dumb. I don't want to say anything that Feynman did is dumb, but it's our dumbed. We dumb it down, right? Dumb that really complicated scattering expression, right, which is the true physics. We dumb it down to diagrams. Okay, so this is not really what's happening at the LHC in our phi-cubed universe. Okay, in a phi-cubed universe, the LHC only scatters phi particles off of each other. All right. Okay. So, anyways, here are the Feynman rules. All right. This is just for phi-cubed theory. Okay. A lot of these will carry over to other theories that we'll look at, but there are some that are specific. Okay. In particular, the vertex rules. Okay. And like I said, when we changed delta, the Feynman propagator, from position space to momentum space, we're making that move into momentum space. Okay, so a lot of times you won't see it, stated explicitly, but 9 times out of 10, when you see Feynman diagrams, they're going to be in momentum space or Feynman rules. Okay. Okay, so here they are. I'll just read them off. Okay. Number 1, draw lines. What we would call external lines for each incoming and outgoing particle. Okay, so that means that if I had so let's consider a case where we have 2 to 2 scattered. Okay, so the first thing it's telling me is that I want to write down 4 external lines. 1, 2, 3, and 4. Okay, for each particle, 2 coming in, 2 outgoing. Okay, it's a specific case. Okay, leave one end of each external line free and attach the other to a vertex at which 3 lines meet. Okay, that's the specific part of phi cube theory. Okay, all right, so that's telling me that I have these vertices that look like this. It's starting to look like a game of Tetris. Okay, so I have these vertices, and I'm going to glue together these the initial lines to the final lines by using vertices, right? Because I want to consider fully connected diagrams. Right? So one possible diagram that I could have would be to connect this guy with that, and that guy with that, and then this guy with that, and that guy with that. Okay? That would give me one fully connected diagram that represents scattering 2 particles into 2 particles. Right? But I don't necessarily have to do that. I could consider, this guy connecting with this guy. Right? See what I mean? We connect them in different ways. Okay? And topologically, they're going to be different. Okay? So that's why I'm saying there in point 2 to draw all diagrams that are topologically inequivalent. Okay? Because that first diagram that I drew is going to give you a different expression than what this diagram is going to give you. Okay? Right? And we just saw that there's only 3, in this theory, there's 3 topologically different scattering diagrams for a 2 to 2 process. And we got this one, and we had this one, and then we had this one. Okay? I think that's how we do it. Okay, so we've got 3 topologically distinct diagrams. Okay? All right. Okay, so now on each of these diagrams, what does number 3 say? On each incoming line, draw an arrow pointing towards the vertex. For outgoing lines, draw an arrow pointing away from the vertex. Okay, so this is, you can do this however you want. I choose to, I like to think of the incoming particles, coming in, and then outgoing particles outgoing. But a lot of times people write down these Feynman diagrams and they define all momenta to be incoming. Okay, you can do that because in the end you're taking modulus squared, so it doesn't matter. Okay. All right. Anyways, so all I'm saying is that number 3 is up to your, you can do it however you want. All right. So it's telling me that these diagrams have arrows coming in. These diagrams have arrows going out. Right? In, out. Okay. Number 4, assign each line its own momentum. Oh, okay. Yeah, I forgot the second part of point 3. For each internal line, draw an arrow with an arbitrary direction. So I can draw it in any direction I want. Okay. To me, it makes sense that a diagram would flow like that. On these diagrams, it really can go either way. Okay, so I'm going to draw it go like that, and I can draw it go like that. Okay, these arrows represent the flow of momentum. Okay, that's what these arrows are supposed to represent. All right. So now, assign each line its own 4 momentum. Okay, so like I said, let me use the notation that I had before, where I have one of these so one of the initial particles has K1, another one has K2, K3, K4. This one again, K1, K2, K3, K4, K1, K2, K3, K4. Okay, everybody with me so far? Yeah? So I'm just following these rules, okay? And now what I need to do is assign momenta to the income or to the internal lines, okay? And there what I do is I make sure that I conserve momentum, okay? So if I have momentum flowing in here, K1, and momentum flowing in here, K2, the momentum flowing out of that vertex is going to be K1 plus K2. Right. Okay. But my delta function tells me that I could also write that as K3, 4, right? Okay, good. Okay. Here I have K1 flowing in, I've got K3 flowing out, so the momentum flowing down is K1 minus K3, right? Because I had K1 coming in and I gave off K3, right? So the momentum flowing down this one is going to be K1 minus K3. But the Dirac delta function tells us that that could be written as K4 minus K2, right? It's always important to keep that in mind, keep energy, conservation of energy in mind, because a lot of times you can simplify a lot of things by making that change, by going back and forth, okay? And so finally, here, this diagram, K1 flowing in, K4 flowing out. So that means this is K1 minus K4. That's good. Okay? Okay, so I worked through 5. Okay, so these are my first part of my Feynman rules, okay? And now I get to the point where I assign factors to different parts of the diagram, okay? External lines. So before, remember when we were working in position space, we had, these dots here, and those were represented by J's, remember? But we've taken functional derivatives, right, and we stripped those guys off, and then we made the change to momentum space, okay? So our external lines now for these fields is just 1. The factor is just 1. Okay? So you don't even have to do anything for external lines. Okay? Okay? Lines, internal lines with momentum K look like that. And that's what Hussein was saying earlier, that those guys, anytime you see 1 over K squared minus M squared, that's coming from what we would call propagator, an internal propagator. Okay? So for example, this first diagram is going to go like, so its momentum is what? K1 plus K2 squared. And there's only one mass that we have, this minus. Right, and you can put in the minus sign, absolutely. Right, but this diagram is going to go like that. There's going to be a factor in this diagram that goes like that. Everybody get what I'm saying? Yeah. All right, so that one would go like the K1 minus K3 and so on. Okay.
Those channels actually, some area is channel.
Yeah, I'll introduce that notation in a minute. Number 7 has to do with loop diagrams. Okay, so what you find is if you go all the way back to the LSZ formula, right, and you plug in some expressions for diagrams that have loops in them, what you're going to find is that there's leftover integrals. Right? That in our case, in our tree level case, it worked out that all the integrals magically disappeared, right? Either through delta functions or rewriting them as delta functions, right? But with loop diagrams, it just doesn't work out, and you're going to end up with one or more integrals left over, right? So if you have a one loop, so a perfect example for us would be this guy, right? The 2-point function, right, with a loop, okay? Because if I apply the rules, so here, let me say, let's call this K, so that means K over here, right? And so I can assign the direction of momentum any way I want, but let me just call this guy that, oops. This guy that, okay? And so let me call this guy L. Right? And so that means that this propagator is going to be, what's momenta? L plus K. Right? So I have this undetermined momentum. There's no way that I can determine it, right? So I have to integrate over it. Okay, so that's what Rule 7 is talking about. And we'll see that later, okay, but it's good to put it down. Okay, for loop diagrams, you have to divide by the symmetry factor. Right, we've already seen the tree level diagrams, you don't have to do that. And if you have loop diagrams, it's good to go ahead and put in these counter term vertices. Okay, so for the 2-point function, you put in that 2-point counter term diagram. All right, so let's see how this works. Okay, so here's what we got. I think I basically, except here I put, so I drew this guy going up and that guy going up too. Okay, but we have our 3 diagrams. Okay, and I've assigned the momentum, I've conserved momentum at the vertices, which determines the internal lines, and so on and so forth. Okay. Oh, I skipped over the other factors, didn't I? Yeah, so external lines, internal lines, and then for each vertex you include a factor of IG. Okay, the counter term for now we can drop because it's not going to come in until we do loops. So every vertex you include a factor of IG. Okay. All right, so now we have our diagrams, we've assigned momentum, we have our rules. All we have to do is write down the amplitudes, right? I have a cheat sheet on my on the side of my desk. It tells me what I write down for each vertex and in each internal line. And this is what the amplitude is, right? And that gives us the T matrix. And the T matrix gives us the S matrix, right? And from the S matrix, we can get cross section. All right, so my IT is equal to what? I've got, each diagram has 2 vertices, right? And each diagram has 4 external particles, 4 external lines, right? And then each diagram has its own propagator, right? So here's the propagator for that diagram, here's the propagator for that diagram, and here's the propagator for that diagram. Okay? And that's it. And if you go back, make sure we don't. If you go back and look at how we computed this thing before, this is the S matrix, so that some stuff got factored out, but it's the same expression. Okay? And you see all the pain that we went through to get to this expression and all the joy that we just went through in writing this down. I mean, it took half a slide, right? I just wrote down some diagrams, assigned momenta, and then applied my Feynman rules, and bam, I've got the T matrix. Okay? So it's that simple. All right? So thank God for Feynman. Okay, all right. I can simplify things a little bit by squaring out all those factors of I. And so I would get that the T matrix looks like that. Okay? And this is the thing that we want to take, and we want to take modulus squared, and then eventually put it into a computer and figure out a number. Okay? But you guys will have to do it by hand. All right? Now, if you want to put it in a computer, that'd be awesome. But we'll see. Okay. I'll show you some tools. When we get there, I'll show you some tools that you can use. And if you want to do everything computationally, that'd be awesome. Okay.
So we calculate loops.
Yeah. Well, no, loops you still have to do by hand a lot. But that's okay. I won't give you too hard. Okay. So this is good. This is great. Okay. But we can actually put this in a simpler form by introducing some notation. Okay. So first, I'm going to introduce or make the point that any external mass, any external particles are what we call on mass shell. So that means that anytime you see any of their momenta squared, that means it's just the mass of that particle squared. Right. So for our case, all the particles have the same mass. Right. Just the mass of the 5 particles. Okay. And then what we can do is introduce this notation called, they're called Mandelstam invariants, but you've probably heard of them. They're S, T, and U. Okay, so S is typically defined as it's a center of mass energy squared. Okay, that's the one that's usually, it's always the same and independent of the process or who's doing the calculation. But it's the sum of the initial or the sum of the final state momenta squared. Right? And they're invariants, so that's what makes it nice because they're Lorentz invariants. Okay, and so you can write them in all kinds of different ways. Right? So you see that in equation 26, in both cases, I've carried out the square, right? And then I've recognized that K1 and K2 squared are M1 squared and 2 squared. So right now I'm being general, but for us, the masses are always going to be the same. Okay? Okay, so what does that do? Well, it lets me write that expression as equation 30. And that looks completely harmless, right? That equation came up knocked on your door at 11 o'clock at night. You'd be like, oh, come on in, little equation. Cute, right? But that represents this really complicated process of these particles coming in and scattering off of each other. Okay? All right? And another nice thing about these Mandelstam variables is that they obey certain relationships, and the one in particular that's useful is that the sum of the Mandelstam invariants, S plus T plus U, is equal to the sum of all the external masses. Okay, that's true for any 2 to 2 process. Okay, and you can go through and you can show it. It's not that hard, by plugging in what S, T, and U are in terms of momenta, and you'll see that it just falls out. Okay, but it's a nice expression, especially if you're working with, some really lengthy. Once you take modulo square of these things, they can get pretty long. Like remember I told you guys, they used to have like sheets and sheets for one process. But you can use tricks like this to eliminate one of these Mandelstam invariants and stuff like that. Okay. All right. So we've got our T matrix. Next would be to take modulo squared, right? And then we can go off and compute the cross section, right? But to do that, we need to stop for a second and take a look at the kinematics of the process. Okay, because if you guys remember from quantum, the expressions for things like the what do we talk about, like not decay rates, but transition rates and in particular cross sections depend on the kinematics of the particles involved. Okay, and so let's take a look and see how they come in. Okay, so what we have is so this is not a Feynman diagram now. This is your classical 2 particles coming in and scattering off of each other. Okay, I'm going to define typically what you do is you define the z-axis to be the axis of these particles coming in and colliding off of each other. And we know from classical physics that this angle phi here is the same as this angle phi. Okay. Okay. And we're working in the center momentum frame. And that means that for the initial state, we have K1 plus K2. And by definition, that has to be equal to 3. That has to be equal to 0. Right? But no, here, notice I'm talking about the momentum, right? The 3 momentum. Okay? So that means the magnitude of the 3 momenta of K1 is equal to the magnitude of 3 momenta of K2. So in this frame, you can write down, you can compute what S is, right? So S is the sum of the 2 4 vectors, right? But the 3 vector parts of these guys cancel each other out, and so all you're left with are the 0 components, E1 and E2, and then you can square it out. Okay, so you can see what S is in terms of the initial energies. Okay, and you can actually write down what E1 and E2 are, because now you know that K2 that appears in E2 is equal to K1, so they're equal. All right. Well, they're equal. Here I'm being completely general, so I'm allowing for these masses to be different. Okay. All right. So I can plug in. I can work with energies. I can work with momenta. Right. I can plug in. So what I do next is plug in E1 and E2 into my expression for S, and I get this. Right. Or I can solve for the magnitude of K1 out of this mess, and I get something that looks like this. Okay. And you're going to say, where is this all going? But you need these expressions, right? Because, if you go back and you look at what these guys are, they have K1, K2, K3, K4 in them, right? And so you're going to need some expressions for them in terms of your lab coordinates or, center momentum coordinates. Okay. All right. And the same thing goes for K3 and K4. They're, because we're in the center of mass frame, right? And I guess so we're in the center momentum frame, so the sum of their momentas has to be equal to 0. So that tells us their magnitudes are equal, right? So the momenta are equal but opposite. And again, we can do the same thing, and we can solve for the magnitude of one of these guys by plugging them into S and so on. So I get an expression that looks like that. Okay, so now I've got an expression for K1, I've got an expression for K3, and I can go off and maybe compute something for this T, right? And make a connection between these kind of, abstract invariants, S, T, and U, in terms of, observable things, okay? So let me take T, it's the difference between the two 4 vectors, K1 and K3, right? But if I square it out, I get something like that. I can use the on-shell mass relation to replace those first 2 factors with masses squared. Right? This is the dot product between 2 4 vectors. Right? So the first term is going to give me E1 times E3, and then there's a minus sign that changes that minus sign into a plus sign. And this is the dot product of 2 3 vectors. Right? But we've got expressions for those 3 vectors. Okay? And then I just simplify a little more by using the normal 3 vector dot product. Okay, and we'll use this in a little bit. Okay, but it's just an example of how you can go from Mandelstam invariants, which are really nice, because they give you really compact expressions, to but they give you a way to get from those Mandelstam invariants to real things. Okay, like the energies, angles, and so on. Okay. All right. So I think we've covered this before in quantum. I'm going to extend it, obviously, because we're working in Minkowski space. But basically, what we want to do is we want to calculate or derive a formula for the cross section. Right? If you guys remember in quantum, there's a lot of hand waving that goes on when you compute these things. Okay, so just accept it and move on. Okay. It's not something to get really hung up on. All right. So we want I can't remember the exact definition. It's the flux of probability, right? The differential cross section. You guys remember when we talked about this? Got chalk falling apart. Got erasers falling apart. All right. We talked about. Some scatter. There we were always scattering off of something that's stationary. But here we're scattering 2 particles, right? And then we have a particle comes out, and then very far away we have some detector, right, that has some spread d omega. Is this looking familiar? Right? And so we're interested in computing the differential cross section, right? And I can't remember. It's the flux of probability. Blah, 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 over blah, 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 blah. Okay? I don't remember the exact definition in words, okay? But it's related to probability. Okay?
Modulus is squared.
Modulus, what squared?
Okay.
Where? This?
Yeah.
Oh, no. I mean, this is just in words what the cross section is. I think what you're thinking of is we wrote it in terms of the scattering amplitude. This. Yeah. This is just the words of what this thing is. But it has to do with probability. Okay. So I'm just going to skip this stuff because we covered it before. All right. But the probability is basically so you have S matrix up top, right? Modulus squared. You have to divide through by the initial and final factors. What else do? You use some other hand waving stuff. Let's just get through this because this is boring. I'll let you read it on your own. And you get down. So here, so first, the first thing you do is you derive, hand wave this way of getting probability, and then you hand wave your way into getting a flow of probability, the rate of change of probability, right? And then you go through, and then you kind of use a lot of air quotes and talk about fluxes and things like that, and then magically you get down to something that looks like this. Okay, so let's just go. Let me just go to this. Okay, because this is what you're going to do in real life. When you compute a cross section, for a 2-to-2 process, you're not going to go through all this bullshit. On these slides, you're going to go and look at the back of Peskin or the back of whatever book you have handy, and you're going to look for the formula, right, for the cross section. That's not the important part. The important part is how to compute that t squared. Okay. All right. And it looks like this. So this is a differential cross section. Okay. The d omega is going to come out of this thing. All right. It goes. That's a typo. It goes like the t matrix squared. Right. And we're in the center mass frame, so there's some factor of the momenta, the initial momenta, and the center mass frame, some square root of s factor, and then our d ellipse. Right. Do anybody remember what d ellipse stands for? Not the D's not included in that acronym, but
Something in phase.
Lorentz invariant phase space, right? Because we're working in Minkowski space, we want our phase space to be Lorentz invariant, and so we went through this big. We actually did it two different ways to show how to write down the Lorentz invariant phase space. Okay. So the Lorentz invariant phase space depends on K1, K2, but really it's going to depend on K3 and K4. Okay. Right? And so this is in general, that's why this n is here. So n represents the number of final state particles. Right? So for us, it's going to be 2. Okay. Right? Okay, so here's where I have what d ellipse is. Okay, so d ellipse is, in general, for a factor of k, it's got that factor 2 pi to the 4, got a delta function, and then these two Lorentz invariant phase spaces. Remember, you uses that twiddle. That twiddle means that there's some factors of 2 pi and other stuff included. Okay. When I say he, I mean Srinivas. Okay. All right. What do I want to do next? Okay, so I'm computing the Lorentz invariant phase space for our 2-to-2 process working in the center mass frame. Okay. So what I do is I remember that E1 plus E2, that's the total incoming energy, right? The total center mass energy, and the total center mass energy is just the square root of S. Okay? And then the sum of K1 and K2, the 3 vectors is 0, okay, because we're in the center momentum frame. Right? If we plug these into those expressions, these differential guys, okay. What do I have? Oh, and I'm plugging into the delta function. All right, so you see a three-dimensional delta function. So this 4-dimensional delta function splits into a 1-dimensional guy that just involves the energy, and a 3-dimensional guy that involves the momenta. Okay, and then you can always change k's with the e's, the energies. Right, you plug those in, and you go through some more steps. Again, this is stuff that I'll let you work through in your own time. Okay, you can. So you get down to the expression I had before, And now you make the change into spherical coordinates. Okay, so you replace any factors of d3k with the normal spherical coordinates, but now you're in momentum space. Okay. And you use some other tricks along the way. So you have to evaluate these delta functions of E, right? But remember, E is a function. So you've got integrals in K, but you've got this leftover delta function in E, but E is a function of K, right? So when you do this last delta function, you have to remember that little trick with the delta function of a function of some variable that you're doing the integral on, right? Which involves the roots and taking derivatives. Everybody remember that trick, right? Yes. Yes. Maybe it's in Jackson. If that helps. Okay. So in the end, so you do some more tricks, blah 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 blah, and you get down to something that looks like this. So this is what my Lorentz invariant phase space for two-particle final state looks like. And you see that it goes like K1 prime, and I think in the process, I just realized I went from a notation where I was using K1, K2 goes to K3, K4. I switched to K1, K2 goes to K1 prime, K2 prime. Sorry. Right? Oops. Make it back here. Okay. So what I have is a Lorentz invariant phase space that depends on the final state momenta, and it depends on this angular piece, right? With some factors square root of s. And if I put it all together with what we had before, so let's go back just to appreciate where we came from. Right? So this is what I got before, equation 55. And now I plug in this d-ellipse piece, and voila, I get a nice cross-section formula in the center of mass frame, just in terms of t squared, right? And the final state, the ratio of the final state and initial state momentum, right? But those things we measure, okay? So when we want to compute a differential cross-section or the full cross-section, total cross-section for a 2-to-2 scattering, this is a formula that you would use, all right? Okay. And this is assuming nothing about different particles or anything like that. This is completely general, so you can use this for any theory. So you can go apply this to QED, right? As long as you know how to compute t squared, you can plug it in there and you're off and running. Okay. All right. Yeah. So this is written in terms of the angular, or in terms of physical coordinates. We can actually, a lot of times you'll see the cross-section written in terms of Mandelstam invariance, right? So that's where we make use of that expression before, where we worked out what T was in terms of the external energies and the angle, right? So let me make the change, and you get a Jacobian out of this change from d omega to dt. You get some factors of K1 and K1 prime, right? But you plug that in, and boom, you get something that looks like equation 60. Again, it goes like modulus t squared, some factors of 1 over s, and so on and so forth. So note that this is the differential cross-section with respect to t, little t. Okay? So a lot of times this guy, if you're asked for, if somebody asks you what's the total cross-section, for 5 to 5 scattering, it's going to be probably a lot easier to work with Mandelstam invariance, right? Because you have, this thing is going to be a function of st and u, right? And then to get the total function, I just need to integrate over t. All right, so it's a lot easier if you're after the total cross section to do it that way. All right. And one last general standard cross sections. Oh, oh god, yeah. So there's another symmetry factor, right? This one you thought you were done with symmetry factors, and it has to do with the fact that if you have identical particles in the final state, we can't tell which particle came from which vertex. I'm saying that, whatever. Right? So you have to account for all possibilities, okay? So that means that we're going to overcount, and so we have to include another symmetry factor, okay? And that comes in, and this is another point of confusion in the real world, because I've done a lot of work on processes where you have identical particles in the final state, and I remember us getting stuck on this, where the symmetry factor came in. Did you put this, do you put the symmetry factor in at this point when you're writing down the final diagrams, or do you put it in at the final stage when you're computing the cross section? And the answer is you put it in at the cross section. Okay, I was right. The other people were wrong. Okay, so you see here I've got the total cross section, and to get that I'm integrating d sigma dt over t between whatever these t min and t max are. And those you can figure out from, the things that right? The initial energies or momenta, or the final energies and momentum that you measure. Okay. Right, so we've got two ways of doing it, of computing the cross section, right? Where we can express things either in theta and s, which is basically the center mass energy squared, or you can work in terms of st and u and integrate over t, right? Where s is, again, it's fixed, okay? What do I want to do here? Let me look real quick. I don't remember what this is. Yeah, let me stop here. Well, let me just skim through it. It's kind of interesting. Where was it? Okay. All right. Okay, so I've been completely general so far, but now let's take the case where all the masses are the same, which is what we have in phi cube theory. Okay. In that case, these expressions simplify a lot. Okay, and we can actually, I'll show you an example of putting this stuff into a computer and seeing what you get out. Okay, so so these are what happens. So you see, like, things like this. Like, remember how complicated this expression was in terms of all the different masses? But if all the masses are the same, it looks like this. Okay, so you can see how simple looking even those really complicated things look like. And you can compute what t and u look like, right, in terms of s and theta. Right? And then I can go back into my t matrix and plug in for t and u. Right? So you see in the second, third diagram, or second, third terms, I plugged in t and I plugged in u in terms of s and theta. Okay? And now we can take modulus squared. Well, let's see, what else are we doing? Computer, yeah. Oh, okay. So I looked at two extremes. Okay, so we look at extreme case where the masses are much greater than the momenta, which is hardly ever the case, or the case where your center of energy, or where the energy, the ultra relativistic, or ultra high energy region. Okay. So I guess I didn't show you. I've got it. I think I've got I might have a file that I could show you guys to show you what the cross section looks like when you take this thing and take modulus squared. Okay, you get kind of a taste of it. Here, this is doing some expansions and things. Okay, but it can get messy. But the nice thing is, you put it into a computer. You put T into a computer, and you can use the computer to. You guys know about these computer things, right? Okay. Yeah, there's computer things that you can put expressions in, and you can work fully analytically nowadays. There's Mathematica and other packages where you can work with these expressions like you have them here, right? Before, in the old days, when I had to walk to my grad school office up a hill both ways.
In the snow.
Yeah, we had to do things differently. We had to do things numerically. But nowadays you can do a lot of this stuff analytically, okay? And so that just showed, what you can do with a computer. This is just with Mathematica. I squared it, looked at the distribution of, that's probably, what is it, the angular distribution, right? And you see, I don't know what you see. Oh, you see it's peaked at the, I don't know, no, so forward and backward. Okay. Yeah. Forward and backward. Oh, because I'm in the high. So this is for the highly relativistic case, and so you get, yeah, I don't know what you get. Doesn't think about it. It's been a while since I looked at this, but anyways, so that's our first real calculation. Okay. And you can go on and plot the total cross section. So back in the old days, before the Higgs was discovered, if you computed a cross section for the Higgs, you'd have to show plots of the dependence of this cross section on the Higgs mass, right? Because we didn't know what the Higgs mass was, right? So we would make plots like this, where you would plot the total cross section as a function of the mass of the particle, right? And what you expect is the cross section to drop off, basically exponentially as the particle gets heavy, because you're running out of kinetic energy, right? Because all the kinetic energy is being converted into these particles. The cross section gets harder and harder to make these particles, right? And so what you find is that any cross section as a function of the mass of the final state particles should exponentially drop off. All right.
I guess it was fairly school then that cross section depends on the phases.
Yeah, exactly. Yeah. So a lot of times you'll hear, that cross section is killed off by phase space suppression. That's just telling you that because the particle's getting heavy, you're running out of, enough energy to make those particles, basically. Okay. So that's it for today. So now I'm to the point where I can maybe assign a homework problem or two or 8. Okay. So let me think about it. Let me see what we can do with phi cube theory, or maybe do phi to the 4th theory or something. I don't know. I'll come up. I've got some problems that I can give you guys. But what I'll do is, it's summer. Some of you guys are studying for qualifiers. Some of you guys are, I don't know what you guys do. But anyways, you can, any homework that's assigned, you can just turn it in at the end of the semester. Okay. But I would, encourage you to, if you want to understand this stuff as we move on, to do the homework, as I give it out. Right? It's not going to be a lot, but, do it when I give it to you. That's basically what I'm saying. Okay. All right. Okay. All right. So have a good weekend. And,